Okay, so now as we go further and further into the PCNSE, we're on section 3, which is all about interfaces. Interfaces, how you configure them, what you configure them for, the different types, and of course you can see here there's several different types. So we've got Ethernet interfaces, which are here, so that's your physicals and your logicals underneath the physicals. VLAN interfaces, we know what VLANs are. Loopback, tunnel, and SD-WAN. Okay, so we're going to start first with configuring an interface and how you configure an interface. So you come in here, and obviously, depending on the version of firewall that you've got, that will depend how many interfaces you have here. So if we click into one that isn't configured, okay, so we've got the interface name there. You can add a comment to it, so you would add it as because I'm still as original as ever. And then we come to the interface type. So by default it selects TAP. So you've got TAP, HA, virtual wire, layer 2, 3, and aggregate. We're going to concern ourselves with the ones that can forward traffic as opposed to the HA ones, which are a dedicated interface. So if you wanted to configure a TAP interface, you configure that there. NetFlow profile to see what's going across it there. Security zone that you'd want to put it in, and this has to be a TAP zone. So in this particular instance, I haven't got any TAP zones, but we can create one, and then just got to type a zone, then put the interface in it there. Okay, so the advanced side of it is going to be everything that you need to then connect to the switch. So link speed, you normally leave these all at auto. Okay, so if we then move on to the next one, which is a virtual wire. Virtual wire is, again, you can have NetFlow attached to it, so you have a NetFlow profile, which security zone it's attached to, and which virtual wire. I don't think I've got any configured, no. So you create a virtual wire here, so in here you would have interface 1 and 2, because if you think virtual wire is basically like hardwiring the two interfaces together. Okay, so you assign that interface to the virtual wire, which are there. Security zone for the virtual wire, and then again we've got this, and then we've got the LLDP here as well, so it will participate in LLDP with the connected switch or infrastructure. Layer 2 interface. We then create a VLAN to attach that to. It's an interface at layer 2. It's a VLAN interface rather than the next one down. And again, you've got the same options there. Next one down, which is layer 3. So this is now layer 3, so it participates in routing. And so you can attach it to a default, not to a default router, you can attach it to the default router, or you can create a new virtual router for it, depending on how complex your routing is going to be. Security zone, and then this course, because it's layer 3, needs an IP address, whether you want to do IPv6, SD-WAN profile that it should be attached to, and again you've got the link settings and then other stuff as well. So you got, because it's a layer 3, it can respond to management requests, or can respond to certain. So for instance, I have ping only, and that means that on that interface the only thing it'll accept is ping requests and respond to. The MTU for it, of course, we know that drop the MTU down if we want to run VPNs across it or anything like that because of the overhead, and then the maximum segment size, you can control that there. ARP entries, if you want to add any static ARP entries, and then you got NDP and NDP proxy, LLDP again, and dynamic DNS. But we are concerned now specifically with just the creating of interfaces and the different type of interfaces. And once we've gone through this and shown this part of it, we'll then go to what you would use those interfaces for, what the use cases are, and that's sort of pretty much what you're going to need for the PCNSE. It then talks about dynamic routing, route flexion, and virtual routers, and so on. So if we have a look at the VLAN interfaces, if we're going to create a VLAN, put the VLAN number in there. That is agnostic of this, but it wouldn't make sense to make that 25 and make this 10. So then you create a new VLAN there, and then again you go into the virtual router and the security zone that it's in, and then the IPv4 for the VLAN interface, because when you created the physical interface, that is just the leading into this VLAN interface. Think of this as, in Cisco world, it's an SVI, I guess. Loopbacks. Use loopbacks for a lot of things. One of the use cases I have here is specifically for the DNS sinkhole, and that is so when traffic is sinkholed, surprise, surprise, it goes to this address, and I can then monitor what hosts are making calls to that address by running a report on it. And the loopback again has the same again, so it's a loopback, the number you want to give it, virtual router it's attached to, and the security zone it's attached to, and then its address. And just a little bit whilst we're here. So for in this instance, I created a loopback 2. It was DNS sinkhole loopback for reporting. No NetFlow profile because I haven't got NetFlow on it. But it has to be reachable for all hosts that are on the default virtual router. And it's in the outside zone, meaning specifically in my case that no matter what zone the traffic is originating from, it has to pass through the firewall and thus get logged, and I can then check it later. Tunnels. Tunnel interfaces are exactly what they say they are. So you create a tunnel interface. This has to be a unique number. Comment again, NetFlow profile again, virtual router again, and then security zone. Now security zone is where this lands. So specifically if you're creating a site-to-site VPN using tunnels and you wanted it to be on a local sort of local to a security zone, you'd put it on the inside zone, let's say, and then traffic that's also on the inside zone would then be allowed to it and from it based on the fact that it's intrazone traffic, and then you'd control that intrazone traffic using the intrazone rule. Or you can land it on another security zone. That's where the tunnel terminates, and then you'd have to control the traffic between that specific zone and all the others. IPv4, bit of a contentious subject. Sometimes you don't need it, sometimes you do. We'll go into that sort of later on. IPv6 again, and then the management profile and the MTU. SD-WAN. I haven't got a license for it, but SD-WAN is where you configure your SD-WAN interfaces, and there's lots of configurations around jitter and so on in order to configure SD-WAN basically. So you create SD-WAN groups, you assign the interfaces to it, and then you create the policies that then move the traffic along one interface or another based on varying criteria. Okay, so that's really the interfaces at the minute. So what we need to do now is just look at the use cases for them, why you would use certain interfaces and what they're for. And for that, we'll move over to the good old whiteboard, and I'll see you there. Okay, so the first one I'm going to discuss is tap interfaces. In tap interfaces, we're not taking any kind of action on the traffic. We're literally just looking at the traffic and evaluating. So we can still evaluate all the traffic that comes through a tap interface. We just don't take any action on it. Okay, so let's just say you have an existing topology. So we have a wee cloud here. From that we've got our router, and then underneath that we have our switch, And then underneath, bad as it is, we have our other vendor firewalls. Okay, and then ordinarily, of course, underneath that you then have another switch that connects into, which we're just going to put there. Switch 2, switch 1. Okay, so our traffic now is flowing from the host down here to the switch and go up there. But your guy there is not happy. He's not happy with the vendor that he's got. So what he wants to do is he wants to then come in and he wants to say, right, I want a, I don't know, proof of concept. There you go, that's one use case. So on a proof of concept, you'd come in with your superior firewall and say, how are we going to see what this is seeing and how this can protect me better against what these are seeing and how they're protecting us. Well, we can't put it in line as a layer 3 because at that point we're moving traffic across it. We could put it in as a virtual wire, but that would still mean disrupting the path physically because we'd have to physically connect the firewall in. So the best thing we do is we create a span port on the switch, connect it to a tap interface on the firewall, and then send all the traffic that we want to evaluate from this guy across to that. It will still flow out that way, of course, because the switch is going to forward the packets on, but it will go to the tap interface, and then here we'll see the logs of everything that the Palo is picking up. So that's basically a tap interface. You'd use it for that, or you'd use it. You could use it just to see what the issues are, I guess. But 9 times out of 10, a tap interface would be used pretty much as a POC, as a way of showing a customer how they are going to benefit from Palo Alto, as opposed to whatever that might be. This one's going to be virtual wire. So in virtual wire, we have our router, our edge switch, and in this really badly organised company, we then go straight down to our hosts at the bottom here. Probably through another switch, maybe. Now it's not ideal, it's far from ideal, but if we also say, just to add some complexity to it, if we also say, coming off this switch we have a server farm, put another one in there as well. Okay. And your particular customer doesn't want to disrupt this IP scheme they've got going, then simply we can take the Palo Alto firewall and we can enforce policies on this traffic as well. So we take our Palo Alto firewall, and we create a virtual wire. So on here, so if we create virtual wire 1, which is our virtual wire, and then we have ETH 1/1 and ETH 1/2. So those are our physical interfaces. And then what we do is we connect them on the virtual wire. We can then put this in here. So you would, in the path, let's say, you take out that. Not the most descriptive of drawings. Take out that, and then this is just acting as a bump in the wire. Nothing down here has any knowledge of anything happening further upstream. This just injects its MAC address into the table, and all traffic flowing from here and here will still go to whatever the interface is here. So 1.1.1.1. Okay, so on there we'd have then what we do support. So we support things like App ID, Content ID, LLDP, because that's layer 2. We can enforce rules on the traffic, we can block traffic based on these, we can evaluate traffic based on user ID. What we can't do is anything that involves a layer 3 interface, because these have no layer 2 or layer 3 configuration. So for instance, we can't terminate a VPN tunnel, can't run DHCP server off it, because these things need to have a layer 3 address. Okay, so that's virtual wire interfaces, and they would work very well for use cases where you have the inability to take down the system, or where they have an already established IP scheme that they don't want to change, because you don't need to change it. You can just insert the firewalls into the path and evaluate the traffic and act on the traffic as well. You can still do HA, you can still do QoS, you just can't do anything that involves a layer 3 network address. Okay, so then layer 2 interfaces, this is what we usually want to have switching between networks. So we have firewall here, we have an interface, and then we're going to create that interface, and that has to be in the layer 2 zone. And then underneath it we'll have sub-interfaces for 1.200 and ETH 1.1.300. And then that'll come down to a switch. Here. And there. Have VLAN 200 and then VLAN 300. Hosts there. And now you can switch the traffic between the two on the firewall based on this layer 2 connectivity, and then you would of course in this particular instance have interface going out there, which can be ETH 1, 2, and that's going to be a layer 3. So these are layer 2, and then they'll switch based on the VLAN header tag, and that's why you have layer 2. And of course the most common type is layer 3. So again we have a firewall here, and on this firewall we may have ETH 1, 2, ETH 1, 3, 1, 4, 1, 1. Okay, and and these will all have IP addresses. So 1.1.2.1, 1.1.3.1, 1.1.4, 1.1.4. Oh, come on, think it through. It's layer 3.1, and then outside we can have a 192.1. And so then they would be broken up into zones as well. So you got, say we've got our zone there, zone there, zone there, and that could be our inside DMZ, and maybe dev zones. This one, of course, is going to be our outside zone, or untrust as some people like to call it, although untrust is, don't really like it because it tends to detract a little from the whole zero trust thing. If you've got a concept of an untrust, and by virtue of that you have to have a concept of a trust zone, and there is no such thing as a trust zone. I don't think we should be trusting any zones. Just quickly, just to reiterate this part, so this here is our north south traffic, and this here is our east west traffic. And so then you would then basically have within here, you have your virtual router. So we have our VR, virtual router, and then in that virtual router you will have the following. So let me find another pen, go with orange. So on here then your routing table would be 0 would be ETH 1.1, and we would have 1.1.2.1, say let's say it's a /24, would be locally connected on ETH 1.2, ETH 1.3, 1.1.3.1/24, and then ETH 1.4.1.4.1/24. Of course, the eagle-eyed, and I am going to correct that now, would notice that that actually isn't the case, because they would all be zeros because they're network addresses and not host addresses. Okay, so in that respect then you've got your VR, your virtual router there, that knows how to get to the internet, and it also knows how to get to these, and it will route from them. So the hosts in here, that would be their gateway, that would be their gateway, that would be their gateway. And again, because of that, we also know that based on the fact that we're looking at the layer 3 information, as a packet comes up here destined for 1.1.2.10, that'll know where to send it. Obviously with layer 3 you have everything, you have QoS, DHCP, NAT, protection profiles, you have your zone protection profiles and your reconnaissance profiles and so on. Everything then is supported by the layer 3 interface, and that's pretty much how you normally, that's kind of your traditional sort of setup. And of course that leaves itself open as well for the floating IPs if you've got 2 boxes, or ARP sharing or something like that. All comes hand in hand with the layer 3 interfaces. Decrypt mirror. So obviously data loss prevention and stuff like that is a very big thing at the minute, and quite rightly so. And although you can do this all within the Palo box, you may have existing infrastructure, or you may have a service that you pay for that you want to then send the packets to. The problem is, of course, that with DLP, one of the main things is being able to see inside the packet, see inside the traffic, and see what it actually is, to ascertain as to whether it's malicious or not, or if there's any data leakage. So in this particular instance, we have our firewall here. Wow, I'm not going to have that. Firewall. Okay. And we have our connectivity going out, our connectivity coming in. Okay, and what we want to do is we then want to go off to what is this in the corner, which is our third party DLP service. So what we can create is we can create what's called a Decrypt mirror. When we create the Decrypt mirror interface, it's a special configuration that goes here. So we have that interface there, Decrypt mirror. And as we're coming across there, and we break it with the HTTPS inspection, so we have HTTPS inspection here. Inspection. We'll then send a copy of that traffic, which is decrypted, across to our DLP service for them to do with what they will. So it basically allows us to leverage the Palo Alto firewall in order to provide decrypted traffic to a third-party service. Now on to aggregate interfaces. So again, we have our firewall. And we have 1, 2, 1.3 for instance. Okay, 1.4 is going up there. Now a switch here. That's a really badly drawn switch. We have a switch here. Okay. Now, so for most times, there's a couple of approaches to this. The first thing to bear in mind is that you have to create an aggregated interface. So what we normally do is 1, 2, 3, going down to the switch, okay? And then these would be separate VLANs, they'd be separate LANs, for instance, separate networks, that type of thing. But if we want more throughput, we want to build resiliency. I'm sure we've all seen diagrams like this. So if I bin this one, so really, in most networks these days, as we said before, this comes down here. We have an edge switch. Obviously you have lots of other stuff going on above it. Okay, and then that edge switch, in fact I'll just draw that again because I need to make that different. Okay, it's coming down from here to, there we go, edge switch 1, edge switch 2, and then underneath there we have our firewalls. And then what we're going to do, because there's a cross connect there as well. So then, then we have underneath, we have core switching infrastructure, and you'll see something along the lines of to that, to that, of course suggesting that we have full resiliency, but how exactly does that resiliency work? Well, using aggregated ports, if we were to simply just have these two coming down here, spanning tree would cut one of them off anyway. So you could argue that as spanning tree cuts one off, if there was anything to happen to that link, then spanning tree would reconverge and it would notice there was a path up the other link and it would open up one of the other ones for forwarding. It's very clunky. Spanning tree is, I detest it with a passion. But what we can do to increase throughput and to have resiliency is create aggregated interfaces. So again, an aggregated interface is a logical construct that sits above the physicals, and you have to create that first. So here we'd have AE0, 1, and then within AE0 we could add Ethernet 1, 1 and 1, 2, and then here we can then have 1, 3 and 1, 4. So once we've created our aggregate interfaces, we then connect them to the bottom, to the switches. And you'll find that in most places they have the concept of a VPC, not Amazon VPC, but the virtual port channel, VPC. Okay, and on this VPC, you have a virtual port channel that's between two switches, and then our aggregated interface will run across them. So what we'd do is here you'd have VPC, 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 VPC. Okay, and we know for a fact that we've got our AE and our physicals. So then we'd bind these two and these two, and we'd bind these two and these two. So in this particular instance, we have 1, 2, 1, 2. And then what we have then is we have the ability to load share across these aggregate interfaces, and also because they're a single interface across the two, should anything happen, say like if that one drops out, then you've still got connectivity that way, you've still got connectivity that way, but crucially as well, anything that's coming in here has still got connectivity that way to the cloud or the internet. Okay, and that's basically what aggregated interfaces are for. They use 802.1ax, which is link aggregation, and that's how they exchange the messages across them, and that's how they keep them going. There's several, when you really want to go into link aggregation, there are several ways in which this is. The hashes are created to actually what traffic goes down which link. Usually is a lot of it is based on source and destination IP address. So if you have, let's say for instance you have let's say you have some hosts down here on the 192.168.1.0/24 network. They come up there and they hit a NAT device, and that NAT device takes everything from there and NATs it behind 1.1.1.1. then up into your link aggregation, everything would then be pinned down one link because it's looking for everything from there. So you'd normally have, so then if we have our switch at the top, all the traffic that's going up, there's two links there, and it's going to use the one of them because that is never going to change. That destination is never going to change unless you come from there and you go into a different NAT, say 1.1.1.2, or if you remove the NAT altogether and then you go up into the link aggregation like that, and then now you would have .1 and then probably .2, .3, .4, 5 and .6, and then so on would then be load balanced across those links. And of course, should one of those links fail, then everything will go across to the single link. These can be different medium types. So you can have an optical, so A1 could be 1.1, sorry, could be copper, and this could be optical. The only restriction you have is that they have to be the same speed. So if this is 1 gigs and that's 10 gigs, that's not going to work. That just it's no. They have to both be 1 gig. Okay, and then that's it. That's pretty much it. And then you attach then, as you attach your functionality and everything to the interfaces, you would attach it to the aggregate interface, and then that would be inherited by physical interfaces underneath, and they can operate like a layer 3 interface because the layer 3 information is on there. Okay, so that's link aggregation. When we look at the PCNSE study guide, they will want you to look into routing and the difference in the different types of routing. And here we are with the virtual routers. So we use the concept of virtual routers. Virtual routers, you can have several virtual routers, and then it becomes quite complicated because you have to, if you need to go between virtual routers, you need to sort of use that as the next virtual router as the next hop. But specifically with PCNSE, it's more around this particular sort of case here, where we talk about the classic, the legacy virtual router, which covers these, and then we have the advanced, which is BGP, and how we configure that, and how we use the virtual routers to enable routing, basically. So when we're looking at assigning an interface to a virtual router, as we saw before, you can see all the interfaces here. Okay, as it goes in, we then have static routes, but we have a redistribution profile as well, so that we can redistribute those routes using a dynamic routing protocol. We have RIP, good old RIP. Don't think anybody uses it anymore. OSPF v3, and then, as I say, for the advanced, we have BGP and multicast. The way to see where the routing is actually is within your virtual, so network virtual routers, more runtime stats, and now you can see the routing table as it is. You can see the routing table there, forwarding table. So this is where everything's actually going to go. So if you're looking for something that's going to go to, say, 10.0.200.1, you know it's going to go to that interface because it's locally connected. There's lots of uses for this because you can troubleshoot things quite a lot, really. Then you've got the flags and the explanations for the flags underneath. It's up, host, gateway, ECMP, preferred path. I have no static routes monitored, so you can monitor static routes and then redistribute that. rip into your RIP configuration, OSPF, OSPF v3. I've got no dynamic routing configured, and the BFD summary information. So that's where you see that's where you see the traffic's going to go, and you can look for the next hop, and you can see the route table as it is. So if we now want to put in a route, static routes. So in this particular instance, I have a network that is on the other side of this this tunnel. So it's a VPN. A bit bigger. That was useless. Right, so I've got a VPN, and the network on the other side of that is the 172.16.200.0. So I need to give that a route so it knows where to go. Now, this is one of the things we're talking about with tunnel interfaces. They don't necessarily have to have an IP address. So if you have a destination route that is down a tunnel and there's no next hop, it will just place that packet in the tunnel. So it knows that if I've got anything going to that network, I just put it in that tunnel and it will come out the other end, and all will be well. And then if you wanted to withdraw that route for any reason, so if you wanted to monitor a path, you could add an IP to ping from. You could use a loopback or whatever, and then a destination IP on the other side. And this is fairly straightforward. You've got just a name for it, source IP, destination IP you're going to ping. So you could pick a host on the other side, so 172.16.200.4, for instance. Then the interval, so how many seconds between, the ping count 5, and it will miss. If it misses 5, it will mark that path as down. Also, there's the metrics and the admin distance, and that gets really involved in routing and how you can weight routes differently to other routes and prefer routes and so on. An important thing to remember as well is that the route table and the forwarding table are two different things. So as a route is received or it is configured in the route table, that isn't necessarily where it's going to send it. If you want to have a look and check and see what's actually going to be sent, because this is the RIB or the routing information base, and then once the virtual router obtains the best route from the routing information base, it then places that in the forwarding table, which is forwarding information, and then that tells you then where that traffic is going to go. And as a side note, I think I can see why I may have had some issues with my Global Protect VPN. However, yeah, and then you can refresh that as well, so you can see as you're looking at it, you can then check and see whether any information has changed. Okay, so we move on to the administrative distance, which is something else it wants you to know about. So when you're configuring a static route, or indeed when you get a route that's that is populated or is presented and learnt from a dynamic routing protocol, or you've redistributed into a routing protocol, you can redistribute it or learn it with an AD figure. And anybody familiar with routing will know what an AD figure is. So you have an administrative distance. So when you set the administrative distance, or you receive a route with an administrative distance, the virtual router, if it has two or more routes to the same destination, it then uses the admin distance to use the best path, and it prefers the lower distance. So if I had a route this way to up through this tunnel, and I wanted to prefer that over a backup tunnel that I had, both tunnels would be up because they would come up by virtue of the keep alives. But in here, it would notice that I have two routes. However, if this one has got an admin distance of 5 and the other one had an admin distance of 10, it would prefer this one. So it would add this route into the forwarding information base, or the forwarding table. And then when that broke, when that stopped, by virtue of either route monitoring or tunnel coming down, it would withdraw that route and it would add the other route into the forwarding information base, giving you effectively a failover. Okay, so route redistribution is, as we said, if you want to redistribute, so you can redistribute or redistribute this particular route, so where it's come from, the destination and the next hop, and the source type, and then that will redistribute it into routing protocols that you're connected with. Simply means you can advertise routes based on locally connected routes or routes to a private network, private lab network, for instance, and you can inject them into BGP or OSPF so that other people, other routers, downstream routers can learn those routes and they know where to go. So conversely, if you want to give external users access to some parts of the internal network, you can also, not that I necessarily think you should, but you could also redistribute your OSPF routes into BGP. I don't know. I say again, I don't know why you'd want to. So moving on from there, you've got equal cost multipath routing. So Palo Alto does support ECMP. It's basically a feature. It enables a firewall to use, in Palo Alto's case, anything up to 4 equal cost routes. So that's 4 equal cost routes to the same destination. So whereas with traditional routing without ECMP, if you had 4 routes, the router would pick one route and stick with that. With ECMP, if they've got all equal cost, it can load balance across those routes and it will use all of them. It will put traffic down all of them. If there is an issue, then obviously you've still got load balancing across the others. It's many advantages, so efficient use of the available bandwidth on all the links, and you can dynamically shift the traffic by altering cost or anything like that, or an admin distance within those, and it will move across. So I mean, if you had to take an interface down, for instance, but you didn't want to break traffic, you could take that interface, you could move that traffic off that interface, take the interface down, do whatever you needed to do, and then you could dynamically shift it back across. So those are the sort of virtual routers. As I say, it's found under the network virtual routers. And I think to be sort of aware of is these ones here. So we'll just quickly go through. So interfaces. These are your virtual interfaces, physical interface, zones. There are different types of zones. You log from a zone, and you can have tap, virtual wire, layer 2, 3, and tunnel zones. They are mutually exclusive, so you can't have a tap interface in a layer 3 zone, for instance. You create the zone for it. Virtual routers, your IPsec tunnels, as we said before. That's still up, good. So then moving on to GRE tunnels. Okay, so GRE is the routing encapsulation. So effectively, it creates a logical link. A lot of people have heard of GRE tunnels before, and lots of people will have used GRE tunnels before in Cisco world and so on. And basically, it creates a point-to-point logical link between yourself and somewhere else. So you can route or forward the packets across it, receive packets across it, and it becomes like not a virtual wire, because a virtual wire is something different, but it allows a packet to packet the egress tunnel. The firewall adds the GRE encapsulation. It doesn't generate a session, and the firewall does no policy security lookup rule for GRE encapsulated traffic. Therefore, you don't need a security policy for the GRE traffic the firewall encapsulates. However, once it receives a GRE packet, it generates a session and applies all the policies to the GRE IP header in addition to that encapsulated traffic. The firewall treats received GRE packet as it would any other packet. And then on to GRE tunnels. Everybody be familiar, most people be familiar with GRE tunnels. Generic routing encapsulation works the same way on Palo Alto, obviously with certain security measures as well that you don't sort of get just on routers. But it's the same thing, same routing encapsulation, and you create your GRE tunnel here, name, the interface is going to initiate or terminate the session, the local IP address, peer address, and a tunnel interface, all the same pretty much as you would have, well, with Cisco, let's be honest. The timestamp 64, there is a couple of caveats with GRE tunnels because, as with all devices, you have to adjust the MSS to allow for the GRE header. If you don't do that, GRE header is 24 bytes. If you don't do that, the firewall will reduce it automatically by 64 bytes. So you've got 40 bytes of IP header plus a 24 bytes of GRE header to allow that to work. And then you do the same thing there. So if you're going to tunnel it, create tunnel interface, and then all the security is applied to that tunnel interface. So that's GRE. So just a little bit about troubleshooting routing. It really does come down to which way you're actually going. I mean, you can troubleshoot routing by more runtime stats. It's pretty much where you go first. So you look at your routing table, see if there's any routes in there, the forwarding table, see if it knows where to forward it to. If you were to want to do this on command line. Okay, so if we just move that to one side there so that we can see these now. Okay, so if I bring across putty session and you show routing route, and that gives us the same as we have in our route table. Back up, I hate it when it does that. I'll do that. So that's the same as in our routing table there. We can see we've got the metric and metrics here, 10. This is squashed because of the size of the terminal window. And you have your flags at the top there and so on. If we put out that, we can do show routing forwarding information base. And then as we can see this, it's going to do it again. As we can see then, this has got the same information again here as we have before. So we have the route, and this is actually literally where it's going to send it, where it's going to send the traffic. And then again, you've got your flags. So you've got up. These are gateways because it's using that as a gateway to that network. So this is unfortunately that's where one of my problems lies. If the route is up, it's a host, UH. Where's the other one? So ECMP we haven't got. And then third path, we won't have any third path entries on here because I haven't got any multiple routes to single destinations. So that's really kind of it. Just if you did want to check, so if you want to make sure you can get to your, here's an interesting one. So if you want to make sure you can get to your gateway, so if I ping my gateway on here, wonder one. Okay, so I can ping my upstream gateway. Now, an interesting thing is I did have a problem recently where I thought that I could ping my gateway. I thought I had connectivity to my gateway, but in fact I didn't, because by default, when you just ping like that, you ping from the management interface. So if I wanted to ping from the interface that's facing that, I would ping from my source, which in my case is 1.200, host, which in this case is, as we said before, 1.1, and then I'm pinging from there. And what I'd actually done was I'd actually made a bit of a boo-boo on my DOS policy and was blocking my own traffic. So that was less than ideal. That really is interfaces. Say I would suggest going to the go into the information, the documentation that Palo's got. So go a lot further into different sort of deeper things. But from a PCNSE point of view, it's pretty much what you need to know. It is fairly straightforward. If you have any experience with routing, you'll find this no different really. And actually, I think it's laid out a lot better than other stuff. So that's it. So that's section 3, which is interfaces. We're going to go on to section 4. Hopefully, it'll be out very soon. So that's that's section 3. If you do are liking this, please like and subscribe. If there's any issues with anything that's on here, then again, let me know. I've got no issue with that. And hope you're enjoying it, and we'll carry on in our quest through Palo Alto to get our PCNSE.